In this video, we'll be looking at growth models. So suppose we have the variable p, which will be standing for the word population, and that will represent the amount of something that we have. So it could be a number of individuals, or it could be in kilograms, or just some type of quantity. So let's write down a differential equation that would describe growth in the amount of p. So that would involve the derivative of p with respect to time. So we have our dp dt. And let's suppose that this growth is equal to, or is dependent upon, the amount that we currently have. So it's dependent on the current population. So we'll write down this derivative is equal to a constant multiplied by the current population p. So we can easily solve that equation by using separation of variables. So let's go ahead and separate the variables. So we have 1 over p times dp equals a times dt. And then we'll integrate both sides of the equation. So we get the logarithm of p is equal to at plus a constant. And then we can solve explicitly for p by applying the exponential function on both sides. And then logarithm and exponential will reduce, and we get p is equal to e to the power at plus c, which is equal to e to the power at times e to the power c. Now this e to the power c is just all a constant, so we can just rename that. We call that capital A, and we get capital A times e to the power at. Now suppose we have an initial condition. So suppose that at time 0, p has the value of some initial population, which we'll call p sub 0. Then we can use that to solve for the constant in our equation. So we have p is equal to p0. So a e to the power a, and then time is equal to 0. So that's equal to a e to the 0, which is just equal to a. So a is equal to p sub 0. Now we'll put all that together. So our population p is equal to the initial population p sub 0 multiplied by e to the power at. So that's just a exponential function. So if we graph our solution, we can see what we have. So here's population versus time. And when time is equal to 0, we're at an initial population p sub 0. And as time moves on, the population is growing. And it's growing at an ever increasing rate because it's exponential growth. There's another way of looking at the growth of this population. So let's return to our differential equation. So we began with this equation, and the basic assumptions were that the rate at which the population is growing is dependent on what the population is at the particular time, and that's just multiplied by a constant a. Let's divide both sides of this equation by the population p. So we do that, then we reduce, and on the left side we have the rate of growth in the population divided by the population, and that's equal to a constant value of a. If we take the rate of growth in the population divided by the population, we can call that the relative growth rate. And so if we're dividing by the original population, sometimes we'll express that as a percentage. So maybe the relative growth rate is, let's say, 6%. That means that population is always growing at a rate of 6%. And then that would, of course, mean that A is equal to 0.06. So that's how the A is controlling the rate at which P is going up. So this original differential equation that we had up here was a model that assumes that the relative growth rate is constant. So if it happens to be 6%, then it's always 6%. Now that is not always realistic. So if we look at our graph right here, we see that we begin with a particular rate of growth, which keeps on going up as time increases. Of course, the relative rate is staying fixed, so the percentage is whatever percentage it was at the beginning will be continuing on throughout the entire graph. But the absolute rate of growth is always going up, and that might cause some problems. So there might be some upper limit up here beyond which population cannot go above. So we're going to now refine our model a little bit and try to include that fact. So go back and consider our differential equation, where we're assuming that the relative rate of growth is a constant of fixed A. And so let's also graph that. So suppose we have the horizontal axis here being P, which is our population, and the vertical axis being our relative growth rate. So under this differential equation, the assumption is that the growth rate doesn't change. So it begins at A, and it stays at A no matter what the population is. So that would be an equation of y equals A. So maybe as a more realistic approach, we could have the relative growth rate going down. So when the population increases, that puts more strains on the environment or on the resources available. And so there's not as much growth potential as we move on. So we could have a relative growth rate that begins at A, but then decreases as our population moves up. So I'm just going to have, just as the simplest case, have a line going from the intercept at A downward. So if that is a linear equation, then it would be y equals, so we'd be in mx plus b, and the slope is negative, so I'm going to write that as negative b as our slope, and that's multiplied by the p, and then our intercept is at A. So that'd be an alternative to the relative growth rate, just something that's linear and going down. So now let's put that into our differential equation. So we have dp dt is equal to, and now taking the place of A, we have this formula right here. So our decreasing linear formula, and then multiplied by that p. So this is a alternative growth model, and this is known as the logistic model of growth. And we'll go ahead and solve this differential equation. So we can solve this by separating the variables, and that means dividing to get all these p's on the other side. So we'd have 1 over, and then we'll have that p there, and I'm going to go ahead and switch those around. So this is going to be A minus BP times dp, and then move the dt over to the right side. So now the variables are separated, and we'll integrate both sides. To integrate the left side, we'll be applying partial fractions. So we'll split up the denominator as something over p and something over a minus bp. And so you can use just various methods to find out what the numerators have to be. One quick way of doing this is called the cover-up method. So with the cover-up method, you look at this denominator and set it equal to 0. So we'd have p equals 0, which would lead us, of course, to the value of p equals 0. And then you go up to here, to this fraction, you cover up that particular factor, and you substitute p equals 0 into the remaining part. So we'd have 1 over a minus 0. So it's 1 over a. And we'll put that in as our numerator. And then you go to the next denominator, which is a minus bp, set that equal to 0, and solve it. So if you have a minus bp equals 0, that leads to the solution of p equals a divided by b. And then you cover up that part over here and put that value into the rest of this. So we have 1 over a over b, which works out to be b over a. So b over a goes in here. So that's a quick way of doing the partial fractions method. Now let's integrate this. So we integrate the first fraction, we get the 1 over a times the logarithm of p. And integrate the next fraction, we have the b over a. And then we have this 1 over a minus bp. Well, it's going to work out to be a logarithm. And because the b is negative, we'll get a negative constant out in front. So it's negative 1 over b times the logarithm of a minus bp. And now going over the other side, we're integrating dt. We get t plus the constant c. Okay, so that solves the logistic equation. And now what we'd like to do is to, well, of course, simplify this and move our way towards solving for p in explicit form. So let's see, one thing we can do is to multiply across by a. So we'll multiply by a, by a, by a, and by a on all terms. So those would go away. We'd have the logarithm of p. And then we reduce the a's, reduce the b's. So that's minus logarithm of a minus bp equals at. Now we have a times c. Now both a and c are constants. So let's just make that into a single constant, and we'll call that c1. Okay, next we'll apply properties of logarithms to combine those two. So that become the logarithm of p over a minus bp. And now we can remove the logarithm by using the exponential function. So we get p over a minus bp is equal to e to the power at plus c1. And this can simplify a little bit. So this is e to the power at multiplied by e to the power c1. Well, e to the power c1 is just another constant. So let's replace that with a single letter. Let's call it capital A. So that's equal to capital A multiplied by e to the power at. Okay, now suppose that we have our same initial condition. So at time equals 0, there's going to be an initial population. And so let's go ahead and write that one down. So we'll have P of 0 is equal to some initial population, P sub 0. And we'll just substitute that into our equation to solve for the constant. So that's P0 is going in place of P. So that becomes P sub 0 divided by A minus B times P sub 0 equals, and then we have A e to the power 8 times 0. Of course, that's just 1, so that's equal to A. So that shows us the value of the constant A. A has the value of P sub 0 divided by A minus B P sub 0. Well, we still have some more work to do. So we have our equation right here. This is the solution to our equation. But P appears in two different places, and we'd like to explicitly solve for P. So we'll do that next. All right, so here's that equation once again. So we had P divided by A minus BP is equal to A e to the power AT. And we just solved for A right here, but it was a little bit complicated. So I'm going to just keep on calling it A as an abbreviation. And now let's solve for P. So we'll multiply both sides of the equation by A minus BP and get A is equal to A e to the AT times A minus B times P. And then do the multiplication. So we'll have A times A e to the AT minus B times A e to the AT times P. Let's get both of the P's on the same side of the equation. So we have P, swing this over, so plus B A e to the AT times P equals our AA e to the AT. So factor out the P. That becomes 1, and that's BA e to the AT. And now we can solve for P by dividing. So P is equal to our, over here, AE, or AA e to the AT, divided by 1 plus BA e to the AT. And now we've solved for the population P as a function of time. So that's our explicit solution. Now what we're going to do is to get this into just a slightly different form. So we're going to, well, one thing we can do is we know the value of A. It's given up here. So replace A now with what we solved for before, which was P sub 0 over A minus B P sub 0. And down here as well. But then that makes the fraction look a little bit messy. So let's multiply top and bottom by A minus B P sub 0, just to clear that out. So in here they will just cancel. So we have A times P sub 0 times e to the power AT. And down below we have 1 times that, so it's a minus b, p sub 0. And then those two would cancel away. So we get plus b, p sub 0, e to the power at. Okay, now let's do some more dividing. So let's divide by, or actually either divide or multiply. Let's divide by e to the at or multiply by e to the power minus at. So then that would remove the e to the power at from here. So it leaves us just an a times p sub 0. And then we'd have our a minus b p sub 0. Multiplied by the e to the power minus at. And then over here, these two would cancel. So we just get plus b times p sub 0. So finally we have the solution to the logistic equation in a fairly reasonable form. So it's still has some constants in there. We have the growth constant a, and we have the constant b, but those just depend on the particular problem. So right now we'll just go ahead and leave those as constants. And let's just study some of the properties that this particular solution has. To start out, let's take the limit of the solution as t goes to infinity. So apply a limit to p. Now as t goes to infinity, that means we're going far into the future, looking at the long-term characteristic of this solution. All right, so t goes to infinity. Well, a is a constant and p0 is a constant, so nothing happens up here. And down below we have some more constants. B and p0 are constants. But the place that t appears is right here. So that's e to the power of, now let's assume that a is positive, so this is e to the power of a negative exponent. And so as t goes to infinity, this factor becomes 0. So this entire first part here goes away. And we get a times p sub 0 over b times p sub 0 is the only remaining parts. And that reduces down to a over b. Now the important part for us here is that this limit is a constant. So a is a constant and b is a constant. And so in the long term, the population approaches this particular constant value. So this is different from exponential growth. In exponential growth, the population just keeps on climbing at an ever faster rate. But here with the logistic model, there's an upper limit to the population. And so in some of the problems, this is known as the carrying capacity, or those call it the limit of the population. So if we make just a very rough sketch of the solution, we'll have p on the vertical axis and t on the horizontal. The population begins at some initial value, which we're calling p sub 0. And for a while, it grows almost exponentially, where the relative growth rate is a, or at least approximately equal to the a that we had over here. But then as we go along, this begins to slow in its growth rate. So there's an upper limit which we approach. So somewhere along the p-axis, we've got an a over b, and we'll just extend that as a horizontal dotted line. And so as we get closer to that line, the growth becomes less. And that's our horizontal asymptote. So the population approaches that line, never actually, at least mathematically, reaches that particular line. So this is roughly the picture we get with the logistic growth. So if the original population is small in comparison to the carrying capacity, which is up here, then the growth can look like exponential growth. So it's growing faster at a rate proportional to the population itself. But as we approach the carrying capacity, then the growth rate has to go down, and that represents our maximum population under the logistic growth.